Hello to our friends joining us via recording. We are starting to review for exam number 1. So to help us prepare for exam number 1, we started with reviewing a little bit of the content that we covered in class yesterday when we were working on lesson number 4. So the first kind of thing that we covered in lesson number 4 were our transport proteins. Now, we already chatted about this a little bit before we split up into groups. When we talk about using a transport protein, what are some of the chemistry words that we use to describe the kind of stuff that goes through the membrane using a transport protein? So what are some of those chemistry words, like how we feel about water or what we do with our electrons? What kind of things use those transport proteins? Yeah, so I'm seeing a comment in the chat that one of our words for the kind of things that go through the transport proteins are polar things. Remember, polar things are things that do not share their electrons equally. So things with a partial charge, they're going to have to go through a transport protein. Hey, if you have a partial charge, that means you do play nice with water. You're hydrophilic. Because remember, water has a partial positive and a partial negative. If you play nice, or if you have a partial positive and negative too, you're going to play nice with water. You're hydrophilic. This would also include things that are called ions, things that have a full positive or a full negative charge. You really play nice with water if you're an ion. And a couple of us also mentioned that the other kind of thing that goes through transport proteins are things that are very large. If you're too large to sneak through, we're going to need a transport protein for you. So these are some of those kinds of things that we use these transport proteins to bring inside. I guess I saw one other. Sorry, let me add that to my list. The other one being water soluble. Water soluble. All right, so I've got a list of these kinds of things that I need to get into my cell, and I need to use a protein to do that. I have 4 or 5 different kinds of proteins that I can use. We're going to go through these statements here to figure out which kind of protein or which kinds of proteins are being described. So let's start with one of the questions that Dr. always loves to ask. Which of my kinds of transport proteins are always open? Who's always open? Yeah, the ones that are always open are the ones that are called leakage channels. Leakage channels. They're that leaky faucet that's constantly dripping, dripping, dripping. Leakage channels, that's the kind that's always open. When we talk about gated channels, any of my kinds of gated channels, they are not always open because they have a gate, right? That's what their name means. They have a gate. When we talk about carrier proteins, there were a couple of things about carrier proteins that we talked about. The first thing we talked about with our carrier proteins is actually this statement right here, right? Carrier proteins are the kind of transporter that actually attach to what they're transporting. So let's add that here. Carrier proteins, they actually attach to what they're transporting. When they attach to what they're transporting, the other important thing about them, like Kira said, is then they change their shape. So they open on one side, attach to something that they're going to transport, then they change their shape and open on the other side, allowing them to transport something. So carrier proteins, not only do they attach to what they move, they also change their shape in the process of moving. And remind me from yesterday, carrier proteins, were they fast or were they slow comparatively? Fast or slow? Yeah, these ones, my carrier proteins, are going to be a little bit slower than my channel proteins. They will probably be faster than leakage channels because those are leaking. When a carrier protein gets going, it gets going good. but it doesn't get going as good as those gated channels. Those were the fire hoses, right? So my fastest ones are these chemically gated or voltage gated or mechanically gated channels. Leakage channels, pretty slow. Carrier proteins also slow in comparison to those gated channels. Talking about gated channels, one of my types of gated channels, you push it open. Which kind of gated channel do we push open, or we use pressure to open it? That might be another way to talk about it. Yeah, exactly. My ones that are mechanically gated, my mechanically gated channels are the ones that we push open. Remember, we use the word mechanical energy to describe how those open. So literally you're pushing it or you're putting pressure on it. That opens up those channels. When we talk about a neurotransmitter opening up our channels, what kind of gate is that if we're using a neurotransmitter? Yeah, my neurotransmitters are chemically gated channels. If you open with a neurotransmitter, you're chemically gated. That's because a neurotransmitter is an example of a chemical. So it may not just be a neurotransmitter that opens up the gate. Maybe it's some other kind of chemical, but anytime it's a chemical key, we call it a chemically gated channel. And when we talk about charges leading to the membrane opening up, what is the kind of gate on a charge opening us up? Yeah, exactly. If you are opening because of charge, you are voltage gated. Voltage gated, absolutely. My last question down here is a little bit of a tricky question because we didn't fully explore it in our class yesterday. We kind of talked about it. There are more than one right answer for this one here that's talking about passive transport. Do we remember what of these transport proteins do passive transport? Okay, so we're saying definitely leakage. We're saying a lot of us are mentioning carriers. So I'm being a little tricky on you actually. Carrier proteins are typically used for active transport. Carrier proteins typically do active transport. So all of the channel proteins, whether you're a leakage channel or you're voltage gated or chemically gated or mechanically gated, all of the channel proteins. Channels always do passive transport. By the way, what does passive transport mean? Again, what's passive transport? Yeah, so a couple of different things that it means. First thing that it means is there's no energy required, right? Passive transport, it takes me no energy. Second, what that means is the reason it takes no energy is because we're going downhill. We're going from high concentration to low concentration. If you're a channel, which means you just open up and stuff moves the way that it wants to, you can only ever do passive transport. Channel proteins can only do passive transport because they never attach to what they're moving. What they move always goes from high to low. If we go back here to our statement about carrier proteins, we said that carrier proteins attach to what they're moving. If a carrier protein attaches to what it's moving, that's going to give it the chance to spend some energy to move it the wrong way. So good examples of carrier proteins that we talked about in last class, the sodium-potassium pump. The sodium-potassium pump, that is an example of a carrier protein because it attaches to sodium on one side, then it opens up to the inside and lets the sodium out. Then it attaches to potassium on that other side, opens up and spits the potassium out. It's constantly changing its shape to allow it to move sodium and potassium in the wrong directions or move them up the hill. The other example of a carrier protein that we talked about is the sodium glucose cotransporter. The sodium glucose cotransporter. And remember, this was the one where sodium and glucose both attached to my protein, and then it opened up to the inside of the cell to bring both of these things inside. So big idea here, when we talk about carrier proteins do active transport. When we talk about passive transport, my kind of protein that does that is channel proteins. I can also do that just going straight through the membrane, just doing diffusion or just doing osmosis. But the only way I can do this active transport thing is by using carrier proteins. So carrier proteins do active transport, channel proteins do passive transport. Hey, speaking of active transport, notice we talked yesterday about two types of active transport: primary active transport and secondary active transport. We also talked about facilitated diffusion yesterday, facilitated diffusion. Can you remind me in the chat, what's some of the important information about facilitated diffusion? What happens in it? How does it work? Facilitated diffusion. Okay, so we're totally right. This is an example of passive transport. Passive transport, absolutely. So when we're doing passive transport, we're going from high to low. Absolutely. So there's no energy needed. And I think a couple of us mentioned as well, facilitated diffusion, we use those protein channels to make this happen. Because if you split its name in half, facilitated refers to my protein facilitator, and diffusion means I'm taking stuff from high to low. Or diffusion means I don't have to do energy to do this. So facilitated diffusion, that's my only one on this list. That's passive transport. Otherwise, we've got our two kinds of active transport. And remember, whenever you see active transport, you should be thinking energy required. So when we talk about who requires energy, that's going to be primary and secondary active transport. Their name tells us that. If you're a form of active transport, you take energy. Hey, if we're a form of active transport, are we going from high to low or low to high? If we do active transport, are we going from high to low or low to high? Across our little hill over here. Yeah, when we do active transport, we're always going from low to high. We're going up the hill. So when we talk about transporting things up their concentration gradient, we're going from where there's a low concentration to a high concentration. So when we're talking about transporting things up their concentration gradient, that's going to, again, be both my kinds of active transport when we're going up. Now, if we're going from high to low, like this statement says right here, if we're going from high to low, that doesn't take energy. That's going to release energy. Actually, that's going to happen all on its own. So this is going from high to low is an example of passive transport. When we talk about going from high to low, that's the work of facilitated diffusion. Facilitated diffusion, going from high to low. Let's look at our next statement here. Our next one talks about using proteins to move things. Which of the processes listed up there uses proteins to move things? Yeah, Elapina is voting all. She's correct. All of these processes need proteins. We have our protein facilitator, or we have our carrier proteins that are changing shape to allow us to move things. So making a protein tunnel, all of these processes need them. Which of these processes specifically uses ATP? Which processes use ATP directly? We break it down. Yeah, so the one that actually uses ATP is primary active transport. Primary active transport. Whenever you think of primary active transport, you should be thinking my cell is using its energy money. And that analogy you have in your notes about how we could do the Great American Road Trip, ATP is like gas. It's the way you get your car to move. So ATP, the only kind of transport listed up here that I use ATP for is primary active transport. I chop up ATP and I can move stuff. Hey, I got some homework questions about this one. When we talk about primary active transport, I actually have two molecules that are both going from low to high. If two things are going up their concentration gradient, I can't use the energy of one to move the other. They're both going the wrong way. So the only way I can make that happen is by chopping up ATP. Primary active transport uses ATP. Hey, which of those processes listed up there is what we use to feed the cell? What do I use to feed the cell? Yeah, feeding the cell is the job of secondary active transport. Remind me in the chat, what did we say a cell's favorite food was? What's a cell's favorite food? Yeah, cells just like most of us, right? They do love them some glucose. So cells' favorite food, glucose. What we're bringing in using secondary active transport, that's glucose. Yeah, Elapine is totally right. The way I get this glucose in to feed my cell, our example of secondary active transport was the sodium glucose cotransporter. Absolutely. So the sodium glucose cotransporter, how I get that glucose inside. What about my last statement here? My last statement talks about polarizing the membrane. How did I make my membrane polarized? Yeah, exactly. Primary active transport, as in the one that chops up ATP. The goal of that kind of transport is to polarize the membrane. Now, polarizing the membrane is a term back from lesson number 2. What did it mean if a cell's membrane was polarized? What's happening if it's polarized? Yeah, so several of us are mentioning in the chat, when we talk about the membrane being polarized, what we're talking about is that I have a different charge inside, type it here, inside and outside, different charges in those two places. Remind me, polarized is good or bad? Is it good or bad for a cell to be polarized? Yeah, polarized is definitely good for a cell, right? Remember we talked about if you lose the polarity, it's called. If we become the same inside and outside, we are dead. That's bad news for our cells. So we definitely need the cell to be polarized. That's why we're willing to chop up ATP to do it. Hey, we definitely need the cell to have food. That's why we're willing to use some energy to do that. Remember, here's one of our big idea takeaways from last time's class. If a cell uses energy to do something, it must be important. It must be important. So anything that we do with active transport, there's got to be an important reason that we're spending energy on it. Whether it's making sure we're fed, whether it's making sure that we can send messages or that we're different inside and outside. If we spend energy on something, it must be important. Before we move on to other topics, what questions do we have about our types of transport proteins or about these particular kinds of transport here? Or you can give me a thumbs up. Are we feeling okay about these? Yeah, Timoteo, go ahead.
So yesterday when we were treating the voltage, active transport and resting membrane protein, it says when we're at negative 70, we're polarization.
Yes. Yeah. So when a cell is polarized, its membrane charge is negative 70. That's correct. Yeah, and that's a good review because we need to know that number for the exam. When a cell is polarized like normal, it's negative 70. The inside is more negative than outside.
At that point, we're using primary active transport to make ourselves be polarized, right?
Yeah, so we used primary active transport to get there, and we use primary active transport to stay there. Absolutely.
Okay, so when we go from polarization, which is a negative 70, to depolarization, what are we using?
So that's a good tie-in, and let me see if the class can help us out with that. When we go from negative 70 up to positive 30, does anyone know what kind of transport we used to do that? Can we make that connection? Yeah, so we started with our chemically gated channels with the neurotransmitters, and then we open up the voltage gated channels. When we're talking about these channel proteins, what kind of transport used channel proteins? Yeah, there it is. The kind of transport that uses channel proteins is facilitated diffusion. Remember, diffusion means we're going from high concentration to low concentration. When you're looking at the graph on a neuron and it goes from negative 70 up to positive 30, it does that because I opened up a channel for sodium, and sodium so badly wanted to go from the outside where there's a high concentration to the inside where there's a low concentration, that all of these positives rushed inside, no energy required, because we were going from where there's a lot to where there's a little. And they brought their positive charge with them. So the process of depolarizing the membrane, we use facilitated diffusion for that. Facilitated diffusion depolarizes the membrane.
Okay, and then what do we use to repolarize the membrane again?
Any thoughts? Put that one to the class. How do we repolarize the membrane? Yeah, Rima's right. It's exactly the same. We're going to use those voltage-gated potassium channels, which are still channel proteins, which means we're still doing facilitated diffusion. But this time, we opened up a channel that transports potassium. And remember, potassium, there's a lot inside, not a lot outside. So potassium is gonna go in the direction where there's no energy required. It's gonna leave. And as it leaves, the membrane charge goes down. So we use facilitated diffusion to depolarize the membrane to bring the charge up. And we use facilitated diffusion to repolarize the membrane. What's critical is which ion are we opening up a channel for? Because if you open up a channel for sodium, that makes your charge go up. If you open up a channel for potassium, that's going to make your charge go down. But either way, those channel proteins are always doing facilitated diffusion.
Okay. All right. Thank you. Thank you so much.
Yeah, you're welcome. I think somebody else put up a hand. Go ahead, Fanchin.
Okay, I just want to make sure that I got this right. So when we use facilitated diffusion, we're using channel proteins. And when we're using active transport, we're using carrier proteins. Is that correct?
That is correct. Yes,
Okay.
That's a great way to summarize it. Absolutely.
Okay, thank
Perfect.
you.
So Kaylin's asking a question here. We're talking a lot about our graphs. So let me just pull it up really fast because it's an important thing for us to review. Let's see, right here. Here's what we were just talking about. So let's label some of the stuff that we just said. What we just said, let's start here. Number 1 represents something called resting membrane potential. Or in other words, what we're saying is that this cell is polarized. Polarized is the word we just used on the previous slide. I should back up in case any of us didn't have a chance to come to yesterday's class or haven't looked at this yet. Can my friends who were here help me out? Can you tell me in the easiest possible way, what does this graph show us? What is this graph representing? Do we know? Okay, yeah, so Fanchin is mentioning this is what's going on with neurons. Absolutely. It has to do with what we call their resting membrane potential. Yesterday, we had a different word that we used. Yeah, there we go. Audrey popped it in for me. Instead of saying membrane potential, remember that yesterday I told you let's mentally change it and change it on our paper to say membrane charge, because that's what potential means. Membrane charge. When we're looking at this graph, what it shows us is what happens to the charge on a membrane from when it's resting, when it's listening for its neighbors to talk to it, to when it receives a message from its neighbors, all the way till it decides to talk, to pass that message on, back down to when it gets back to rest, back to normal. So some of the things that we just talked about, making the cell polarized, making the cell be at -70, how we get here is using primary active transport. So let me make that note over here. Primary active transport is what helps us to be polarized. In particular, what we talked about was the sodium-potassium pump. So what makes my membrane polarized, what makes me start at -70 is the sodium-potassium pump. And the sodium-potassium pump is an example of primary active transport. At this point on my graph, we have it labeled stimulus applied. What did we say in easy words happened at this point on my graph? Rather than using this weird stimulus applied, what was the easy thing or the simpler way we described this? Yeah, I like it. The word that we used yesterday was message. This is when a neuron gets a message, like a text message. Or if we're being more specific, because these are neurons, what we're actually seeing happen right here is a neuron is receiving a neurotransmitter. Its neighbor is sending it a juicy piece of gossip that it needs to pass along to its neighbors. So it receives that neurotransmitter. That neurotransmitter is a kind of chemical, which means that we're opening up what kind of channels? If I used a neurotransmitter to open it, What kind of gate do I have down here? Yeah, exactly. Down here I've got chemically gated channels, Somebody had mentioned for me, how do we keep track of what ions are on which side of the graph? You just got to memorize it. So over here, we're talking chemically gated sodium, or Na+, chemically gated sodium channels. Chemically gated, we open with a chemical, a neurotransmitter. I know it's sodium because sodium makes my membrane charge go up. When I open a channel protein for it, my membrane charge goes up. Here we go, my favorite. We're going to draw our salty banana cell because we got to know this to understand our graph, right? We're talking about sodium right now, talking about sodium. Where do I find a lot of sodium? Inside or outside? Where's the sodium? Yeah, sodium's on the outside, right? And hey, sodium, when I use it to make salt, it's also with chloride. So sodium and chloride on the outside of my cell. And when it's a banana, which ion is on the inside again? What do I have a bunch of on the inside? Exactly, potassium. All the potassium on the inside. Remember, this matters because when we're thinking about the way things move in a channel protein, because all this stuff here that we're talking about on a neuron, all of this is channel proteins. So all of this is always going to move stuff from high to low. So when you're thinking about the salty banana cell, sodium wants to come inside because there's a lot of it on the outside and not a lot on the inside. Chloride wants to come inside too. A lot of it outside, not a lot inside. Potassium wants to leave because there's way too much inside, not as much outside. We must know our salty banana because that tells us if I open up a chemically gated sodium channel, sodium is going to come inside. And sodium brings its positive charge with it and makes my membrane more positive. Remember that when we get to threshold, when we get to -55, we are now far enough away from normal, from resting membrane potential, that now I'm going to open up the kind of gated channels that open up when my charge is wrong. Which kind of channels open up when my charge is wrong? Yeah, it's voltage gated now, voltage gated because my charge is wrong. And we're still doing, like several of us said in the chat, we're still doing sodium. It's still voltage gated, it's still sodium channels. Now they're voltage gated. They are still going to let sodium inside, sodium with its positive charge, raising the membrane potential or the membrane charge all the way up to +30. When my neuron gets all the way up to +30, it has that moment of clarity. Oh my gosh, my charge is completely wrong. I gotta get this under control. I've got to come back down. We're going to open up a new kind of voltage-gated channels. Which kind of voltage-gated channels are we now opening up when we're way too positive? Okay, so we're mentioning the two kinds that I talked about yesterday. First kind that I'm going to put on my graph here is voltage-gated potassium. The job of voltage-gated potassium channels is to spit out potassium. When we spit out potassium, that takes the positive charges away. We're doing subtraction. So I spit out positive, spit out positive, spit out positive, all the way to get me back down to where I want to be. That's the way that I do a process we talked about yesterday called repolarization. Repolarization. The other kind of channel that I mentioned yesterday that we'll care more about in unit number 3, but a couple of us remembered it for today too. We also have a kind of channel called voltage-gated calcium channels. Calcium channels. Does anyone remember what we talked about the job of voltage-gated calcium channels? It actually wasn't anything to do with charge. There was something different that those voltage-gated calcium channels helped us to do. Yeah, exactly. Several of us are mentioning this is the kind of channel that helps neuron spit out neurotransmitter. A voltage-gated calcium channel, we'll talk about this more again in unit number 3. This is what I use to get my cell to spit out its neurotransmitters. So when we're up here at positive 30, when my charge is completely wrong, the main reason that I make my charge wrong is to open up these channels. My goal of making my charge completely wrong is to get me to spit out neurotransmitters. But once I'm that wrong, I have to get right again. I've got to repolarize. So my voltage-gated potassium channels help me to repolarize. Remember though, here's why we're on this graph, how we got on this bunny trail. Whether we're talking about chemical gates or whether we're talking about voltage gates, whenever we talk about channel proteins always do facilitated diffusion. Channel proteins always do facilitated diffusion. So the fact that my membrane charge goes up happens because I opened a channel for sodium and sodium went from high to low. The fact that I opened up a channel protein for potassium and my charge went from high to low is because potassium wanted to leave. Potassium wanted to go from inside the cell to outside the cell. The reason that we have to know the salty banana is because it tells us which way stuff wants to move, and that's going to tell us what happens to the charge on our membrane. So going up and going back down, that's examples of facilitated diffusion. Getting to this resting membrane potential, -70, that's an example of using primary active transport, of using energy to make sure that my cell is different on the inside and the outside. I need to pause to give you all a chance to process and to tell me what questions we have. Or to shoot me an emoji that tells me how you're really feeling. Doesn't have to be a thumbs up. For those of you who can see the chat, do you like our progression of faces? We're going from an upside down smile to a not impressed face to a slightly sad face to almost crying. I feel like that's kind of how my day goes in the morning, right? From when I wake up to to the end of the day. So Ella Pina asked the question, carrier proteins never do facilitated diffusion. I'm not going to say never because I don't know everything. For the sake of our class, the carrier proteins that we're talking about, we are always going to say that carrier proteins do active transport. So for the sake of our class, we're going to say that they never do facilitated diffusion. If you're your bio for majors teacher tells you differently, then trust them. But for our class, we're going to say never. The voltage gated calcium is at positive 30. So positive 30, my charge up here at the top, this is where voltage gated calcium channels open. This is also where voltage gated potassium channels open. So here, let me draw a little arrow. I should have typed that one up higher so as not to confuse us. Right here at positive 30, we open two kinds of channels. We open the voltage gated calcium channels that help us to send the message, but we also open the voltage gated potassium channels to help us get back to normal. The only thing that opens at negative 55 right here are those voltage gated sodium channels. They open up at what we call threshold. That's the voltage that opens them. The voltage that opens these is positive 30. So it's different charges that open different channels. Good questions. Yeah, go for it, Christina.
Okay, so on the last couple slides, you said that the carrier proteins are active transport. Does that mean all of the gated proteins, like voltage gated, mechanical gated, and chemical gated, are those also carrier proteins? Because then on the top you have channel proteins are always do facilitated diffusion. So I'm confusing myself.
Yes, so the key is when I had here, so let me put my, I should have written the full name of these proteins. So it's a voltage gated potassium channel protein, and it's a chemically gated sodium channel protein, and a voltage gated sodium channel protein. So all of these kinds of gates that we're talking about, the gates don't make these proteins carriers. The gates just mean I put a barrier in front of my tube. When I move that barrier out of the way, stuff just goes straight through the tube. So all of these gated proteins are channel proteins. When we talk about carrier proteins, the only example of carrier proteins that we're going to do this semester, the sodium potassium pump and the sodium glucose pump. Those are the only carrier proteins. Yeah, so everything else we're talking about is a channel. Correct. Yeah. Yeah, you're welcome. That's a question I get every semester, so that's you're totally good. Thank you for reminding me to mention that. Yeah, carrier proteins and channel proteins, they are all transport proteins. But carrier proteins, we just have two examples, the sodium potassium pump and the sodium glucose pump. Those are my only two carriers. Everybody else that we're talking about on this graph here, everybody else is channels. It's all channels. Okay, so Callie's asking a question I'll put to the class. She's asking, which channel do we use to decrease the charge of a neuron? Which channel makes my neuron's charge more negative? Who do I use to make the channel more negative? Yeah, potassium channels. It's those voltage-gated potassium channels. They do the process that I mentioned here called repolarization. That's getting the membrane charge more negative. So voltage-gated potassium channels make the membrane charge more negative, or they do repolarization. I think I had another question. So somebody had asked what was happening at parts number 1 and number 6. And I think we kind of helped each other out with this, but at times number 1 and number 6, where it says we're at rest, this is when my cell is at resting membrane potential. So when it's at its normal charge, waiting to hear a message from a neighbor. So to help us have this resting membrane potential to be negative 70, we've got our sodium potassium pump that's pushing that sodium out and pulling that potassium in. But this is when a cell is waiting to hear from its neighbors at time number 1 and time number 6. This is when that cell, to use our word from before, this is when our cell is polarized. Yeah, and someone mentioned the word as well. We have in our little dip at the bottom, we have something called hyperpolarization. Hyperpolarization. That's this right here. Remember, like we said yesterday, whenever you see hyper, we should be thinking too much or extra, a lot. When a neuron is hyperpolarized, it's even more negative than normal. So if you notice on the graph how this part goes under -70, it's even more negative than -70. That's the cell is extra negative, more negative than it needs to be. So we're going to go back up to rest. We're going to get back to normal using the sodium-potassium pump and using the leakage channels to get us back to normal. So in this period here that we call hyperpolarization, we're more negative than we need to be. We're hyperpolarized. We'll use that sodium-potassium pump and we'll use our leakage channels to get back to normal. These are all great questions. What other questions can we think of? I should have used more different colors. I'm going to put some boxes and try to make it a little more obvious. I think somebody had asked, I'll add this other label to our graph here, depolarization. Depolarization is what's happening on this side of the graph. When my membrane charge gets more positive, we're depolarizing. When we're getting more negative, we're repolarizing. When we're too negative, we're hyperpolarized. I need some emojis. Tell me how we're feeling now. Give me some emojis. Yeah, so Elapina asked a question about our voltage-gated channels. We'll talk about that more in depth in unit number 3. So this neuron, when it gets to positive 30, it spits out a neurotransmitter, and that neurotransmitter goes to a different cell. That different cell would do this graph all by itself. So this shows me what happens in one cell. We're going to do the exact same thing in a neighbor. So this is where we go from cell number 1 to cell number 2. The neurotransmitter would go to cell number 2 that's got its completely own graph doing exactly the same thing. I think I've officially blown everybody's mind. We don't even have emojis for Dr. Ellis. Yeah, so Fanjin, calcium is what I use in my first neuron to make it send a message to the other one. Absolutely. Yeah. And again, we'll talk more about this in unit number 3 when one neuron talks to another. Kira asked if we need to know about the calcium channels for this exam. I don't think that you do. If they're not included in the lesson number 4 outline, which I don't think they are, we don't need to know them for this first exam. We will need to know them in unit 3. We won't need to know them extensively in unit number 1. Yeah. Yeah, so Summer asked the question, so no channel proteins use active transport. That is correct. Yes. No channel proteins do active transport. Carrier proteins do active transport, but channel proteins do not. They only ever do passive transport. All right. I want to take us back in time. We've talked a whole lot about this graph, right? About those channel proteins, about all that stuff. I want to take us back to when things were much simpler, back when we were talking about passive transport, when that was all talked about, was just passive transport. Yeah, we're missing the good old days, right? Week 1 and 2. I was chatting with somebody and they're like, man, week 3 is when it got real. No joke. Yep, this is the lesson that we did the tea analogy in. Yeah, we were all sweet tea people, right? I think is what we talked about. Remember how back then when we were doing sweet tea, you were like, man, this is so hard. And then we hit lesson number 4 and you're like, oh my gosh, really? So let's go back to the simpler times and we'll talk about some simpler stuff here. The top of this slide says passive transport, passive transport. Let's remind ourselves of all the things that we know when we say passive transport. Can you help me out in the chat? When I say passive transport, what are you thinking? There's a lot of different stuff we're thinking here with passive transport. Okay, I love it. So some of the stuff we're thinking here, one of my examples is diffusion. Absolutely. We're thinking no energy. We are thinking facilitated diffusion. Yep, facilitated diffusion, another example. And osmosis, someone said. I know someone else told me we're going from high to low. High to low. Perfect. Okay, so just this keyword passive transport here. We've got a lot of different ideas that go into this. When I am looking at these two things, and you remember back from week 2 when I cracked the really corny joke that we got the original YouTube right here in our class, my 2 YouTubes here are showing me a couple of examples of passive transport. These 2 tubes are showing me the processes of diffusion and osmosis. Now, when I look at this first tube up here, so here's what we started with on the left. Here's where we went. My goal of, here's a term that we'll see pop up soon, or pop up again. The goal of diffusion and osmosis is what kind of solutions? So now remember, what is the goal of diffusion and osmosis? What tonic word do we use? Yeah, Tien, Rima, we're remembering. The goal of diffusion and osmosis is isotonic solutions. Isotonic solutions. When I use that word isotonic, what does that even mean? What's isotonic? Yeah, isotonic, we've got equal concentration, or we're balanced. Yeah, I love these kind of things. Same thing. I love it. Samesies. I'm totally putting that on the slide. Samesies. Love it. Okay. Whenever we talk about diffusion or osmosis, my 2 kinds of passive transport, my goal is to get things the same. There are 2 ways to get things the same. I look at my tube right here. We are not the same. This side over here has like 5 things in it. This side over here has like 10 or 15 things in it. Let's use our tonic words. Let's review our tonic words. We're going to get to isotonic, but right now, what tonic word would you use to describe this solution compared to here? What tonic word describes this one over here with just the 5 things dissolved in it? Yeah, this one over here is what we call hypotonic. Hypotonic. Remember, hypotonic means below concentration or a lower concentration. So the one on the left is called hypotonic, which means the one on the right is called what? What's this one with like 12? What do I call that one? Yeah, exactly. I'm going to call that one hypertonic. Hypertonic. Okay, so I've got two solutions here. One of them is hypotonic. One of them is hypertonic. My goal with diffusion or with osmosis is to make them isotonic. Over here, they're isotonic. They both have the same concentration. Now, they both have the same concentration because something moved. Can we tell when we compare this tube to this tube? What is it that moved from one side to the other? Yeah, perfect. We're using our chemistry word here. The thing that moved were our solutes. Our solutes. Remember that word solute is just a fancy word for dissolved things. One way I can make two solutions that are different from each other, one way I can make them equal is I can move the solutes. I can move the stuff that's dissolved in the liquid. When I move the solutes, what did I call that when it was the solutes moving? What was that called when the solutes move? Yeah, exactly. When the solutes move, I call that diffusion. So diffusion is when I move those things that I had dissolved in the water. They're going to go from the hypertonic side, where there's a whole bunch of them, to the hypotonic side, because there's not very many of them over here. So one way to get the concentrations the same in the two sides of the tube is some of these little solutes, these little dissolved things, go from one side to the other. That's one way to make it equal. Here on the bottom is the other way to make it equal. We start off with the same tube that I see right here. We still made our concentration equal, meaning my solutes are spread out just as much on the two sides now. I didn't move the solutes though. What did I move to make these two solutions equal? What moved? Yeah, exactly. What moved is the water. We can also move the water. Yeah, or more technically, like Audrey said for us, we can move what's called the solvent. I moved the water. See, over here, my little solutes are all spaced out. There's lots of space in between them. Over here, they're all crammed together. If I give some of this extra water from this side over to this side, now I still have all of those extra solutes over here, but I have more liquid to make them more spread out. So when I'm moving the liquid, what did I call that process? When the water moves, or when the solvent moves. What was that one called? Yeah, that one was called osmosis. Osmosis, when the water moved. Either of these get me to isotonic solutions. Either I can move the dissolved stuff, or I can move the solution, the stuff that it was dissolving in. Either way, we get isotonic. Either way, we get equal. So when you're thinking about diffusion and osmosis, remember the goal is for these things to get equal, either by moving water or by moving the things that are dissolved. Now, we talked about this in the context of red blood cells. So let's bring back those red blood cells. We talked about this with red blood cells. When we put red blood cells in different kinds of solutions, water can go in or out compared to how those solutions look when we compare it to the fluid inside a cell. By the way, what's the name of the fluid inside a cell? What's that called? Yeah, exactly. The fluid inside a cell is called the cytosol. So as we fill in these blanks right here, I just want to remind you, whenever we use tonic words, we're always comparing one thing to another. When we talk about these solutions here, we're comparing it compared to cytosol and compared to cytosol. Way too long to type. Compared to cytosol. There we go. Okay. When we are looking at these solutions, notice in my picture over here, this first solution, I've got my cytosol inside the cell, and I've got my fluid on the outside of the cell. Water is leaving the cell. So the cytosol must have more water than the plasma, or than the stuff that's on the outside of the cell. If there's more water inside, that means that there's more salt on the outside. And when we're talking about this fluid out here, if it has more salt, yeah, Fanchin's totally right, Elapina's totally right, we would call this one hypertonic. Hypertonic. It has more salt in it than the inside of the cell does, meaning that it's going to steal the water that's inside that cell. This, by the way, is bad news for you, because see how our cells are getting all shriveled up? Because the water that was inside goes to the outside. Bad news. Hey, it's also bad news if the water that's on the outside goes inside. What kind of solution would lead to this, where the water on the outside rushes inside? Yeah, now we're on the opposite extreme, right? Hypotonic. Hypotonic. That means that there's more salt inside my cell than there is on the outside of my cell. If there's more water outside my cell than on the inside, that water wants to go inside. It wants to dilute the cytosol that's in here. Wants to make it the same. Doesn't matter if it's putting too much water in there and actually makes the cell explode. It's going to keep going until we're equal, or until we explode. Bad news. What we want is for the amount of water that goes into the cell to be equal to the amount of water that goes out of the cell. What kind of solution has equal concentrations? Back to our word from before, right? Yeah, exactly. Isotonic. Isotonic. Absolutely. So we want the concentration of water to be the same inside and outside. We want to be isotonic. I saw some notes in the chat that are totally correct. If we are hypotonic, you all read about that. When we read about water intoxication, too much water, and that causes some cells in our body to swell and die. Water intoxication. If we don't have enough water, if we're hypertonic, that's going to happen because we're dehydrated, because we haven't been drinking enough. So there's more water in those cells than on the outside, making it leave. So hypertonic and hypotonic, neither of them are good for your cells, because the cells are either giving their water away or getting too much water. The amount is the same inside and outside when we're in an isotonic solution. I think I saw somebody mention this in the chat. Let me see if I have, oh, I guess I don't have that picture anymore. Let me try one more place. Nope. Okay. So here's the statement that somebody else put in the chat. We'll put it on this slide here. And it's in your notes, so you got it big and in bold. Water follows salt. Water follows salt. That is an underline highlight star idea. Water follows salt. Meaning, whichever solution has too much salt, that's the direction that water's going to go. So check out this statement up here, because this puts it into our special tonic words, into our chemistry words here. Our statement is water moves from the hypotonic solution to the hypertonic solution. Let's make some notes for ourselves about what these different words mean. If I am hypertonic, what does hypertonic mean again? Hypertonic. Yeah, hyper is going to mean more, right? More concentrated, or we could say that it's higher. We've got more solute. Absolutely. A hypertonic solution has more salt. It's more concentrated, which is going to mean it has less water. And I'm more concentrated with salt. I should put it here, salt. Or I have a higher salt concentration. By default, I'm going to have less water there. If I'm hypotonic, that means that I have more water, or I have a lower concentration of salt if I have more water. So when we talk about water moving, water is going from where there's more water, which is a hypotonic solution, to where there's less water, which is a hypertonic solution. When water moves, what was the name of that process again? What did we call it when water moved? Yeah, absolutely right. We call that osmosis. When water moves, we call that osmosis. Okay, so in osmosis, water moves from where there's more water to where there's less water. Does osmosis require energy? When I go from there where there's more water to where there's less water. Yeah, we're right. Osmosis, no energy required. No energy required for osmosis, because what's moving is water, and water's going from where there's a lot of it to where there's a little bit of it. Osmosis is an example of passive transport. Yeah, and Fanshin's asking, is this an example of facilitated diffusion? The short answer to that is yes. Most of the water that goes in and out of your cell will use a special kind of transport proteins, a special kind of channel. I will not ask you about this on the test, but I'll give it to you just so you know what it's called. Aquaporins are the special type of channel protein for water. Aquaporins, the channel protein that we use to transport water. But the big takeaway for us when we're thinking about osmosis is that osmosis is passive transport, because we're going from somewhere where there's a high concentration of water to where there's a low concentration of water. Again, I need to pause. What questions do we have about this? Yeah, Kaylin says, I can handle this lesson. I know I saw some chatter before about, oh, this is so easy. Tell that to yourself about 2 weeks ago. 2 weeks ago, you're like, my mind is blown. Look at how far we've come, right? We're growing. That's the goal, is to grow. All right, I've got about 20 minutes left. So for those of us who are here, I want you to tell me what we want to spend the rest of our time today talking about. I could talk about those chemical bonds if that's what we're most interested in. Okay, Tammy Taylor's saying the bonds. Is any got some agreement on that, or any other topics that we want to focus on? Because I can totally spend the time doing bonds if that's where we want to go. I feel like we need another emoji break here. My first semester online we used to do dance parties. We would do like flash mobs. So if you all pull up your emojis, let's, so here's my flash mob emoji right here. Let's have a little flash mob in our chat. Find me an emoji that represents you dancing, or you with what you would like to look like when you're dancing. Let me see if I can find what it's more realistic, what it looks like when I'm pretending to dance, trying to dance. Here, let's search. This is probably more what it looks like when I pretend to dance. Flailing octopus, let's be real. Nice, Audrey does the robot. I'm a fan. Last semester, I had a friend who used to always send me this one here, not for flash mobs, but just every day for fun. Had I told you all, we said that was Mushu from Mulan. So I used to get a lot of Mushu last semester. That was fun. Nice, I like that, Caitlin. The 1-2 step. That's perfect. All right. So let's talk bonds. There are some things that, and we reviewed some of this in class yesterday. There's some basic ideas with bonds that I hope after yesterday's stuff we are really familiar with. I like that, Kaylin. It's Bond time. James Bond. Electron Bond or something like that. That sounded cooler in my mind before I said it. When we talk about bonds, first thing that we absolutely must know, and we talked about this yesterday, when I form chemical bonds, what am I sharing or what am I transferring? What is it that I use to form bonds? Chemical bonds form with, absolutely, with electrons. 100% of the time it's with electrons. It is never with protons. It is never with neutrons. So I promise you, if you're taking the exam and you see an answer that talks about sharing protons unequally, that's one of those moments where you're like, pshaw, I know that's wrong, and you can automatically ignore that answer. I promise you, by the way, when you're taking that exam, every question with all of the answers on there, there is something specifically wrong with all of the wrong answers. That's why I told you earlier, before we started group work, if you look at an answer and you feel like it's wrong, it probably is, because there is legitimately something wrong with every wrong answer. So if you see something about atoms sharing protons, if you see something about atoms sharing neutrons, we know right off the bat that's completely wrong. Not going to happen. The only thing that atoms share is electrons. Remember that when you're looking at an atom, we've got our nucleus in the center, and that's where we have our protons and our neutrons. And we've got those electrons that float around on the outside. That's the other reason, by the way, that it can only possibly be electrons that are shared, because that's the only thing that's on the outside floating around. When you're looking at molecules, things that are attached to each other, when you're looking at molecules, you can look at the shape of their electron cloud to get an idea of how they're sharing their electrons. So over here on the left, we have a non-polar covalent bond. Let's remind ourselves here with the terminology, whenever we see the word covalent, what did I tell you we should be thinking of? The word covalent, that always means the same thing. Yeah, covalent always means sharing. Always means sharing. So two kinds of covalent bonds that we can see here. Two kinds of covalent bonds. We've got non-polar covalent and we've got polar covalent. So let's start with our non-polar word over here. What does non-polar mean in the context of a bond, a non-polar covalent bond? Yeah, absolutely. A non-polar covalent bond, like Tien said, is we're doing equal sharing. Equal sharing. Non-polar covalent bonds, is an equal sharing bond. See how the size of the electron cloud around each of these atoms is about the same. Notice too how their electron clouds are overlapping. So I see one big cloud where those electrons are zipping back and forth around both of these atoms. Non-polar covalent bonds, equal sharing. Sometimes though, we've got a little bit more of this polar covalent bit going on. Polar covalent, what did polar mean in the context of a polar covalent bond? Yeah, there we go. Several of us are chiming in. A polar covalent bond, these are unequal sharing. This is 100% what's going on between my daughter and my son right now. For any of you who are parents, you know that there is no toy so awesome as the toy that younger sibling has. So like my daughter won't care about a stuffed animal at all until my son picks it up. And then she's like, that is my favorite stuffed animal. Like literally she'll say that, but he's my favorite, but I'm playing with him. It's like, no, you're not, but now brother has him. So you really want him. Yeah, Kaylin says it'll be like that forever. I'll brace myself. Yeah, so this unequal sharing stuff, that's the stuff of siblings. If we've got electrons that are going to be shared, somebody's going to get them more often than somebody else. At least we're still kind of sharing them. Well, we are sharing them. It's not kind of. We are actually sharing them. It's just that one of my atoms gets them 2 or 3 times before they go back to the other one. So we circle around both nuclei, but we spend more time around somebody. Polar covalent bonds. Notice when we look at an ionic bond down here, in an ionic bond, see how there's 2 separate electron clouds? How do we, help me out in the chat, how do we form an ionic bond? What happens in an ionic bond? Yeah, I like it. So we're putting it as politically correct as possible, right? We transfer electrons, or we give away electrons. I'm just saying, Dr. Ollis is feeling a little more salty right now. I'm going to say we're stealing electrons. Let's just be real. There's some theft going on right here. So in an ionic bond, what happens is this atom had an extra electron or 2. And this atom over here said, hey man, I really want those, like give them to me. And it steals those electrons, making it look negative. So this one over here lost those electrons, now it looks positive. Remember, what holds together an ionic bond was the idea that opposites attract. So if you're positive and you're negative, I want to be close to you because we're opposites to each other. Remind me in the chat though, if we put something with an ionic bond in water, what happens? If I put something with an ionic bond in water, yeah, exactly. If I put something with an ionic bond in water, we go through the good breakup, right? The big breakup. Yeah, it goes bye-bye. Absolutely. This one says, oh, water has some positive dipoles. I love that. This one says, ooh, water has some negative dipoles. I love that. And they just split up. They're just done. An ionic bond, a stealing bond, these ones are going to separate from each other in water. The only thing that holds these together is somebody has a positive and somebody has a negative. So if you put new positives and negatives around, these are going to fall apart. Yeah, but Elapina mentioned here with my polar covalent bonds, remember, this is still a sharing bond. Anytime we share electrons, even if we're not sharing them equally, even if there's unequal sharing, like a polar covalent bond, as long as we're sharing electrons, water can't split us up. So a polar covalent bond survives being placed in water. Now, these polar covalent molecules, they're going to surround themselves by water. There's going to be positives and negatives on all sides because they've got a partial positive and a partial negative. They've got those things that we called dipoles. dipoles. So a polar covalent bond, a molecule that's polar, it would spend time around water. It's going to completely surround itself in water, but it's not going to split up because we're sharing electrons. When we stole electrons, this is not going to survive water. It's just not going to happen. What if we're equally sharing our electrons? What if we're nonpolar? How do we feel about water? What happens with water if we have nonpolar covalent bonds? Yeah, like it, Kaylin said, eek. Yeah, we're definitely hydrophobic, right? We want nothing to do with water. If we are equally sharing our electrons, we've got no dipoles. We've got no partial positive and no partial negative. And water has partial positives and partial negatives. So when we put something that's nonpolar with no charges next to something with charges, nonpolar things are like, I don't need that kind of negativity in my life, or I don't need that kind of positivity in my life. I'm good. We're equal here. So nonpolar things are hydrophobic things. They don't want to be around water because they've got no charges. Polar things are hydrophilic things. They like to be around water because they've got the same kinds of partial charges as water does. And things that have ionic bonds, they like water too. I mean, they really like water because they're willing to give up on their ionic bond to be with water. So polar covalent bonds and ionic bonds, these are found in molecules that are hydrophilic. They both want to be around water. Non-polar covalent bonds, found in things that are hydrophobic. They don't want to be around water. I know I've gotten several email questions about why we form different kinds of bonds, because there's some questions that talk about them, specifically talks about the electronegativity differences. Remind me in the chat when we are talking about electronegativities, what does that mean? What does electronegativity even mean? That's a big chemistry word. You can be mad at the chemists. Electronegativity. I like it. Yeah, Rima says it's how much we love our electrons, or Mateo mentions how much we need electrons. Absolutely. If you have really high electronegativity, you really want electrons, like really, really badly. If you have a lower electronegativity, you don't care as much. We can see when we look at, oh, did I take out that chart? I must have taken out the chart. You've got the chart in your notes that shows the color-coded table. Some atoms really want electrons. They're going to be in the dark blue or the dark green colors. Those have a really high electronegativity. Some things have a really low electronegativity. Those are things that are red or orange on the chart. When we put together things that are completely different colors, so they're on opposite sides of the table, their electronegativities are really different. If you have two things that are trying to connect with each other that have really different electronegativities, they're going to form an ionic bond. Somebody's going to give away an electron, somebody's going to take an electron. So when we're on opposite sides of the table, we're going to form an ionic bond. We have very different electronegativities. When we have kind of different electronegativities, so they're somewhat different, I think that's the terminology from the homework. If they're somewhat different, we form what's called a polar covalent bond. Remember, polar covalent, we don't share equally. We're still sharing, but somebody has a higher electronegativity than somebody else. Somebody gets them a little bit more. If our electronegativities are pretty close to the same, so a small difference in their electronegativities, we're going to share electrons equally. If you know the kind of chemical bond that two atoms are making with each other, you can predict if their electronegativities are close or far away. What I mean by that is if I tell you that two things form an ionic bond together, you would know that those things have really different electronegativities. Or if I tell you that things formed with a non-polar covalent bond, you would know that those things have very similar electronegativities, because it's the difference in their electronegativities that will determine which kind of chemical bonds that they form. Yeah, so Audrey asked, will something like that be on the exam? Wink, wink, nudge, nudge, possibly. That's a way of taking electronegativities and applying it. So there's two ways I can ask you electronegativities. Either I can tell you these things have really similar electronegativities. What kind of bonds are they going to form? Or these things have really different electronegativities. What kind of bond are they going to form? That's the first way I could ask the question. The second way I could ask the question is, these things made an ionic bond together. What's up with their electronegativities? Or these things made a nonpolar covalent bond together. What's up with their electronegativities? So as you're studying that, think about it both ways. There's two different ways to ask the question, right? I can either ask it from the bond perspective or the electronegativity. Yeah, so Caitlin asked about this one over here. Let me see if I can remember our exact terminology from the homework. So in an ionic bond, we would say that they are very different electronegativities. When we talk about a non-polar covalent bond, we'd say very similar electronegativities. When we talk about polar covalent bonds, I believe the way that we describe them is somewhat different. Somewhat different. If we were putting them in order from most or from least to most different, least different, so very similar or the same with a non-polar covalent bond. Somewhat different or kind of middle of the road with a polar covalent bond. Very different for an ionic bond. So if you know them kind of in that order and you kind of pair them with this terminology, very different, somewhat different, very similar. That's probably the best way to think about them. I think that's about all I'm planning to cover for today. I will be happy to cover more stuff on Monday if we have more ideas of stuff we want to talk about. I know earlier someone had asked about hydrogen bonds. We didn't get to hydrogen bonds, so I'm going to make a note for myself to make sure that we do hydrogen bonds on Monday. Yeah, Summer asked about the lab material on the lecture exam. That's correct that I am not doing lab material on the lecture exam. The only exception being the functions of the organelles. So use your lab packet. I think it's lesson number 2 that has you outline the function of each of the different organelles in the body. Use that, or in the cell, excuse me. Use that list of functions to restudy that, just to refresh yourself on what the organelles of the cell do. That's showing up on lecture and lab. Other than that, no other lab material will be included on this exam. Yeah. Here, let's put up a whiteboard so that I can give you some important info about the test really fast. Okay, so exam number 1, that's what we're taking, right? Exam number 1 opens Monday at 12:01 a.m. If you want to stay up super late Sunday night and take it first thing Monday morning, it's there for you. It's going to close Tuesday at 11:59 p.m., meaning you need to be done with it by 11:59 on Tuesday. You have 75 minutes to take this exam. I believe it has like 56 questions, so should be more than enough time for you to take the exam. This exam is going to covers lessons 1, 2, 3, and 4 from the lecture. It also covers those extra activities that we did. So we did brown fat versus white fat. We did water intoxication. I think those were the only articles we did this unit. So those things are also included on here. Yeah, so a couple people caught it. Yeah, it's about 50, 56 questions, I think, something like that, 55, 56 in that ballpark. Before you take the exam, before the exam is going to show up for you to view it, you need to install Proctorio on your computer. In the chat, give me a thumbs up if you have used Proctorio before, or if you've installed it on your computer. How many of us have had a chance to do this? Yeah, Helopina says, I managed to do it. Okay, so there's several of us that have done it before. If you have not, there's instructions on how to install that extension on your computer. Once you've installed that extension, there is a Proctorio practice test in the test folder. If you click on that practice test and it tells you you need a password, what that means is Proctorio is not working currently on your computer. So in the test folder, there's a document that says like Proctorio troubleshooting or something like that. It's a list of 11 different steps you can go through to get Proctorio working. So I know it's crazy. Like you can go through and just install Proctorio and then you try to take the practice test and it's not activated for some reason. Just go through those steps to see if you can get it to activate up for you. So anytime, whether it's you're trying to do the practice test or you're trying to take the real test, if it tells you you need a password, that means that Proctorio is not working. I don't have a password. I can't let you in because Proctorio makes it up. So make sure to get Proctorio activated. There's that practice test. Also, even before you try to do the practice test or before you try to take regular tests, there's a thing in that folder that says Secure Exam Proctor. Secure Exam Proctor. Every single time before you try to complete something that says remotely proctored, go ahead and click on this thing, Secure Exam Proctor. It's supposed to make sure that Proctorio is activated. So you click on that, it's going to take you to a screen that's black and white. Just then click the back arrow and you should be good to go. Yeah, Fanshin asked in the chat, can we try this now? Yes, you can. That's the purpose of the practice test. So it's up there, it's available right now in the test folder. If you go in and click on it, if Proctorio is not working, again, it's going to ask you for the password. So if it asks you for the password, go back, click on this Secure Exam Proctor, or use that troubleshooting document to go through and do those steps to get Proctorio activated. Yeah, so Summer asked a good question. If your internet kicks you out of the exam, or if something happens when you're taking the exam, what I need you to do is contact Proctorio right away. They have the ability to get you back into the exam. I do not have the ability to get you back in. So I'll make sure that there's a note on our bulletin board that I post for the week. I think it's something like proctorio.com/student help or something. I'll make sure there's a link for it. If you get kicked out of the exam for some reason, go over there and live chat with someone. They'll get you back into the exam. For any of my friends with a Mac, my students tell me every semester, you need to make sure if you have a Mac to put it in like do not disturb or something like that. Because what will happen is if somebody texts you or emails you and it tries to pop up on your computer screen, Proctorio will kick you out. So please make sure you're not going to have emails that pop up during the exam. Make sure that you're not going to have text messages or chats that are going to pop up during the exam, because if that happens, it's going to kick you back out. So make sure you're in do not disturb. Make sure people are not texting you, calling you, all that jazz. Caitlin, in terms of the guidelines for taking the exam, you just need to make sure you can't have anything on your desk. You can't have other people around you. It's an open, or it's not, it's a closed notes test. So open mind, closed notes. So just make sure there's not stuff on your desk. Make sure you're not referencing your phone. It will flag that for me. If it sees you looking away, it's going to flag that for me. And then I got to go through and watch you awkwardly take your test. And I don't want to have to do that. I want to let you be private. So I'm not sure on if it's turn off notifications or do not disturb. Yeah, I would say, like Chris said, might as well just turn it all off just to be safe. Yeah, Kaylin says, so can I wink and stuff at the camera? You can. Ironically, it's going to watch you. And if you do a bunch of super weird stuff with the camera, it might flag you anyway. So then I might have to go watch you wink at me, and that'll be awkward all around. Christian asked a good question. If you talk to yourself, that's okay too. Again, I'm not going to listen to you. So talking to yourself is fine. Talking on the phone is not fine. I typically tell students, if you would like a blank piece of paper to draw your salty banana cell or to make notes for yourself, that's okay. But what I need you to do is hold up that blank piece of paper at the beginning of your test. So when it first pulls up your test screen, show me that your paper is blank, front and back. At the end of your test, when you're right before you click submit, please hold up your paper for me and rip it up so that I see that you're done with it. So if you would like that piece of paper, I will let you do that. Again, just make sure to show me it's blank at the beginning and make sure to show me you ripping it up at the end. Yeah, and I mean, if kids, so I know someone says that proctoring is making you feel anxious. Here's what I'll say. I totally get that it's not the ideal environment to be taking tests in. If Proctorio flags your test that it seems like weird things went on, I joked about not wanting to watch you. I'll just go in and make sure that there's not something fishy going on. I totally get it if a dog starts barking, if a kid starts asking questions. I'm a parent too. I'm a real person too. So if things like that happen, trust me, it's okay. I will see that and it's not going to be a problem. So just do everything you can to keep the exam secure. But I get that it's not the same environment as if we just had a classroom. So you're totally fine. Don't worry about that. Kaylin, it's going to limit you to one screen. So that's just a heads up. It's going to give you one screen that otherwise it's going to lock the other one down. Ideally, Christian, if someone rings your doorbell, hopefully someone else can answer the door for you. Walking away is definitely going to flag your test. So try not to have to leave in the middle of the test. Yeah, so Kayla, if you're using that bigger screen, maybe just see if you can turn off the other screen, because it's going to limit you to one screen. Any other questions that I can help you with? Yeah, Caitlin, are you using a desktop or a laptop? Because you're mentioning with the two screens, a laptop. So perhaps try in your settings, see if there's a way to transfer what you're looking at. Instead of extending your screen from one to another, see if you can transfer. Yeah, so just play around with it. You've got some time to figure it out. Yeah, so give it a try, and you can try with the practice test too. You can take that practice test, by the way, as many times as you want to. So I would recommend before every exam that we take, go in and take that just to make sure Proctorio is working, because that's a great way for you to check to see if it's working. All right, well, I'm going to go ahead and shut off the recording. If you have any questions, I will stick around in the chat for a couple of minutes here. Otherwise, I'll be here on Monday at 1 o'clock to do one more review session. I know we wanted to talk about hydrogen bonds. If you think of other things you want us to chat about, please send me an email. I'll make sure I've got pictures to do that. Otherwise, good luck with all of the many assignments we have that are coming due on Sunday. Please check out your checklist. There's a lot due on Sunday. So work through all of that stuff. Good luck with your preparations. And I hope to see many of you back in class on Monday.